All right, in this chapter we're going to work with vectors, and you probably recall working with vectors a bit in the last semester. So we're going to start with a little bit of review and just remind ourselves that a vector is a quantity that has both a magnitude and direction. We're focusing on vectors in the plane, two-dimensional vectors. So the magnitude, so the vector here is drawn in blue. The magnitude is the length of that vector, and the direction is the angle as measured from the positive x-axis. Usually in textbooks they'll use a bold V or a bold letter to represent a vector to indicate that it's a vector quantity. That's sort of harder to do when we're writing out by hand, so I'm sticking to the convention of using a little arrow over the letter to indicate that it's a vector. Its magnitude is the length, and it's the absolute value of the vector. So when we talk about, or when we write out or see this written out, it just means the absolute value, the magnitude. And it's common to indicate a vector just by giving its magnitude and direction in a sort of shorthand, like so. We're going to see some examples. If we add vectors, we're gonna learn or relearn how we add vectors sort of more precisely, but graphically, geometrically, when we add vectors, we add them tip to tail. So over here in the diagram on the right, we have a couple of vectors v and w. Those are drawn in blue, and if I wanted to find the sum v plus w, one way to do it is to simply say I'm traversing the v vector, and then I'm just sort of sliding the w vector so that it begins. It's not rotating at all, but I'm just sliding it so that it begins at the end of the v vector. And where it ends, like where the ending point here, is where the end of the resultant vector is. So the black vector, the one that's drawn in black there, that is the vector v plus w. Vector addition is commutative, so here, in this figure I drew it so that v was drawn at the end of, so that w was drawn at the end of v, but we could have done it the other way. I could just say I'll take this v vector and I'm just going to slide it up so that it starts at the end of the w vector. And regardless of what order you do that in, you'll end up in the same spot and get the same sum. And in fact, if you draw them both ways, you get this parallelogram drawn in the plane. If we multiply a vector by just a number, which we call a scalar, it just changes the magnitude. So if I have a vector v here on the left, there's my vector v. Now if I multiply it by 2, just the number 2, it'll just make it twice as long, but it doesn't change the direction at all. If you multiply a vector by -1, it flips the vector around sort of 180 degrees. So there's negative v. I didn't change the length because it's -1 v. If it were like a -2 v, it would be flipped around and be twice as long. In order to make some more precise calculations, we're going to use the components of a vector. So if you look at a vector, in fact, I'm going to scroll back up here at the beginning. We define a vector and always give the vector using magnitude and direction. However, once you draw a vector, if you have a given angle, theta, and a length, it'll end at a certain point, right? And the coordinates of the point where it ends, those are the components. We call the x component bx and the y component by, or another letter, if it was w vector, there'd be wx and wy. But the components of the vector are just the coordinates, the x and y coordinates of the point where the vector ends. And back from the first semester, you probably recall these formulas that I could find the x component by taking a magnitude times cosine of theta, and the y component we find by taking the magnitude times sine of theta. These are both just a result of using SOHCAHTOA, right triangle trigonometry, when you draw a vector and drop down the perpendicular. So this length here, this is Vx. This length here is Vy. And if you use SOHCAHTOA, for example, if I use the cosine, SOHCAHTOA, cosine theta, is Vx over magnitude. And if I solve for Vx, we get Vx is magnitude times cosine theta. And if I use the sine part, sine theta, opposite over hypotenuse says it's Vy over magnitude. And that means that Vy is magnitude times sine theta. So if you have a hard time, remembering these formulas or remembering which formula goes with which component, you can kind of always recreate it. Just drop down the, if you sketch the vector, drop down the perpendicular, you can use SOHCAHTOA. So let's do an example. We're going to find the components of this vector that has a magnitude of 5.88 and an angle of 130. Now, a lot of the time when I'm starting a vector problem, I might just really quickly sketch this vector. It doesn't have to be super. It doesn't have to be like super accurate. It just needs to be roughly accurate, mostly because I just want to place it in the right quadrant. So this is maybe about 130 degrees, and it's at 5.88 magnitude. So I'm just sketching it out because I'm going to expect, by looking at this, I know that Vx ought to be negative. The x component should be negative, the y component should be positive. So we're going to get 5.88 cosine of 130 degrees. I'm going to make sure my calculator is in degree mode. It's in radian mode right now. We get negative 3.78. And for the y component, we're going to take magnitude times sine theta. Uh, 4.50. And then usually I just stick to however, when I give a final result, I'm just finding the components. I'm using the same number of significant digits they used when they gave the magnitude. Alright, so in this next example, a toy wagon is pulled with a force of 85 newtons, exerted on a handle that makes a 20-degree angle with the horizontal, as shown. So 85 newtons directed in this way. What is the effective force for moving the wagon forward? So the first thing I just want to say here is, in nature, there are no coordinate axes. In nature, when you just sort of look around you, you don't see coordinate axes imposed on things. It's up to us to impose coordinate axes on things. So you could, looking at the wagon from this side, we could say, oh, it's kind of like a second quadrant vector. But if we just got up and walked around to the other side of the wagon, it would look like this, and we could still kind of treat it. That's maybe a big angle. We could still treat it as a first quadrant vector if we like. They just want the effective force for moving the wagon forward. So giving that as a positive force, I think, is appropriate. But if you treat this as a second quadrant angle and get a negative number of newtons, because the x component would be negative in the second quadrant, that's fine. But we can kind of simplify it just by looking at the wagon from the other side. And if we want the effective force for moving the wagon forward, that means that we want the x component. So magnitude times cosine of 20 degrees. Oh, 80, oops, not 8, 85. And then, so let's see, 85 times cosine of 20, 79.87. Or if you want to round to the same number of significant digits as they used in the magnitude, we could round that to 80. So when we know the magnitude and direction, finding the components, it's just a matter of using those formulas. We can also go the other way around. If we know the components, we can find the magnitude and direction. If we know the components, we can get the magnitude by using Pythagoras. The components are the two legs of the right triangle. The magnitude is the hypotenuse. So using Pythagoras just means we're going to take the square root of the sum of the squares. And then finding the direction, we have to be a little bit careful. We're first going to find a reference angle, which I'm calling alpha here. And we find a reference angle by making sure that we plug in positives to the arctan. We're using arctan because if I know the components, I'm just going to sketch this out on the margins here. And I'm going to draw this in the first quadrant, but it's valid regardless of where we draw it. But if I have a component here, I'll call that alpha. Alpha is always in the first quadrant, as it turns out. So if I have Vx, Vy, then this is Vx, and this is Vy. SOHCAHTOA tells us that tan of alpha is Vy over Vx, opposite over adjacent. So when we find alpha, we're going to take arctan. Now, the arctan function won't give you every angle that you might want. It will never give you an angle in the second quadrant or third quadrant. It'll only give you first quadrant angles, and it'll also give you fourth quadrant angles, but it'll be expressed as a negative first quadrant angle. So the type of values you get back are kind of restricted. So the way we get around that is we say, okay, I'm going to make sure that I find this this reference angle that I know is in the first quadrant that we're calling alpha. And we do that by making sure we plug in positives. So regardless of the signs of the components, you're going to just make sure you plug in positive values to arctan. And then we find the angle that we're looking for by making the necessary adjustment, just like we learned in the last chapter. Right? If I want a second quadrant angle, I'm going to take 180 and subtract alpha. Okay, so in example 3.3, we want to find the magnitude and direction for the vector with the components Vx is 4.2 and Vy is negative 3.8. Now, I'm just going to sketch this positive x, negative y, I know that I want a fourth quadrant angle. And that'll be important. So let's start with the magnitude. You'll notice here I left off the negative. When you square something, it's going to be positive anyway. So I just kind of left it as positive. However, if you did put in the negative, you just have to make sure that it goes in parentheses. Otherwise, it'll do subtraction instead of addition inside the radical. So we have 5.66. And for the angle, we're going to find the reference angle first. So arctan of positive Vy over positive Vx, or absolute Vy over absolute Vx. So arctan of 3.8 over 4.2. (42.1 degrees), and that means that the angle we want, since it's in the fourth quadrant, is 360 minus 42.1 degrees. And that's 317.9 degrees. So there it is. We found the magnitude and the direction. And then usually I kind of put it together in one nice kind of package, so that our vector v is 5.66 at an angle of 317.9 degrees. All right, so now we're going to add vectors. We've already seen earlier on, a few pages ago, that graphically or geometrically we add them tip to tail. And that can be a nice kind of interpretation of what we're doing, a good way to visualize what we're doing. But it kind of lacks a bit of precision. So to get a precise answer, we're going to use the components to add vectors. So suppose I want to add vectors v and w, and we're going to add them. We're going to get a resultant vector that we call r. Okay, so just this basic relationship here. We're going to call the resultant vector r. Here's how we do it. We're going to find the x components and y components for the given vectors v and w. So get their components. Once you have those components, you get the x components for r by adding the x components together. You get the y components for r by adding the y components together. And then once you have your components for your resultant vector, you use, just like we did in the last example, use Pythagoras and arctan to get the magnitude and direction of your resultant. When you're finding a vector, when you're doing a problem whose answer is a vector, you always want to give your answer by providing the magnitude and direction and not just the components, unless it specifies otherwise. All right, so let's do an example. We're going to add these two vectors. Vector v is a first quadrant vector at 30 degrees, the magnitude of 1210. And vector w is a third quadrant vector at 250 degrees, magnitude 985. So let's find our components. We'll work with the v vector first. So magnitude 1210 times cosine of 30 degrees. That's 1047.89. And the y component, 1210 times sine of 30 degrees. Is 605. Okay, so now let's do the same thing for the w vector. Wx is its magnitude 985 times cosine of 250. That's negative 336.89. And wy is 985 times sine of 250. That is negative 925 60. And we'll just note that the components jive with where we know these vectors are. V is a first quadrant vector, and both those components are positive. W is a third quadrant vector, both of those components are negative. And now we're going to find the R, X, and RY, the X and Y components for the resultant vectors. Now we get the X component by adding the two X components together. So 1047.89 minus 336.89 is 711. And over here for RY, we're going to add VY and WY. So that's 605 minus 925.60 is negative 320.60. Okay, so now a lot of the work is done. We still have a bit to do. We found the components for our resultant vector. Now we need to find magnitude and direction. So we'll just note that the X component is positive, the Y component is negative, so this is in quadrant 4. Now let's finish up by finding magnitude and direction. The magnitude is the square root of the sum of the squares. So that gives us 779.94. And now to get the direction, we're going to first find that reference angle. So the reference angle is arctan of, and I'm going to put the Y component over the X component, making sure everything's positive. So positive 320.6 over 711. For alpha, get 24.3 degrees about. And so we're in quadrant 4, so that means theta is 360 minus 24.3 degrees. And that's 335.7. So now the sum of the vectors. I'm going to give a final answer, kind of tying these two bits of information together. The resultant vector is 779.94 magnitude at an angle of 335.7 degrees. Right, let's do one more. Here they want us to add these vectors. They've given us 3 vectors, and our technique that we learned to add 2 vectors works for 3 vectors as well. It works for as many vectors as you want to add together. The first thing you're going to do is find all of the X components and all of the Y components for each of your vectors. You add your X component to get your R sub X. You add your Y components to get your R sub Y. And then once you have your 2 components for Rx and Ry, you're using Pythagoras and arctan to get the magnitude and direction. So let's begin. the first vector, I'll call this V1. So V1 has a magnitude of 0.750 at an angle of 15 degrees. V2, and I'll label V2 as this vector over here in quadrant 3. That'll be V2. Its magnitude is 0.265. However, its direction is not 12.4 degrees. They gave us, this is actually a reference angle they gave us, but this is a third quadrant vector. So the angle I want is actually that angle right there. So let's see, theta 2, the theta for V2 is going to be 180. I can see that's 12.4 degrees beyond the 180. So plus 12.4 degrees. That's 192.4 degrees. And over here, V3, they gave us, we know that its component, or its magnitude rather, is 0.548. However, its direction, again, they gave us not the actual angle that we need to use. They gave us not the reference angle that we're used to. A reference angle is always from the horizontal, is always from the x-axis. They gave us an angle measured from the 270. So if we want this angle, which we do, then we're just going to realize that theta 3, the angle for this vector, is 270 plus 74.4 degrees. And that's 344.4 degrees. Alright, so now we have all of the information we need about our three vectors, and we need to find the x and y components. So I'm just going to kind of, I think, organize this in a little bit of a table. So V1, x component, y component. For V1, this is 0.750 cosine of 15 degrees. So V1x is 0.724. The y component is 0.750 sine of 15 degrees. So V1y is 0.194, and those are components for V1. Now we'll do the same thing for V2. Our x component, magnitude times cosine, so 0.265 cosine of 192.4, V2x, and the y component will be 0.265 times sine of 192.4. Alright, so let's do the x component first. 0.265 cosine 192.4 is negative 0.259, and for the y component, 0.265 sine of 192.4 is negative 0.0569. And then our last vector here, let's see, x component, magnitude times cosine, and magnitude times sine For the x component first, 0.548 cosine 344.4. And that's 0.528. And for V3y, 0.548 sine 344.4 is negative 0.147. Okay, now what we want to do is just add up the x components to get the x component. So Rx is V1x plus V2x plus V3x, and Ry is V1y plus V2y plus V3y. So for the x component, we're going to add these three together. Let's see what we get. 0.724 plus a negative 0.259, I guess I could have just subtracted, plus 0.528. You get 0.993. 0.993. And for the y component, we're going to take these values and add them together. 0.194 minus 0.0569 minus 0.147, and we get negative 0.0099. Alright, so now we have our components. The rest of this will go like the last example did. We have the Rx and Ry, so we're going to find magnitude by using Pythagoras, the square root of the sum of the squares, so 0.993 squared plus the negative 0.0099 squared. Whoops. We get 0.99305, I guess, approximately. And let's see, Rx is positive, Ry is negative, so again we've got a fourth quadrant vector here. Theta will be, since it's in the fourth quadrant, I'm just going to go ahead and make the correction all in one go, so 360 degrees minus arctan of, and then I'm going to plug in positives here, the Ry positive 0.0099 over 0.993. And that's 359.4 degrees. So this is just a skosh below the positive x-axis. It's almost on the positive x-axis itself. It's just like a hair below. So the resultant vector is a magnitude of 0.99305 at an angle of 359.4 degrees.